Let's first focus on a 2D case, or particularly cleaning up the summation in each term of the series. Because of the two sets of I factorial and n minus I factorial in the denominator, it might remind you of these binomial coefficients. Well, we can do this, just that we need to take in the original 2n factorial in the numerator and get rid of the extra n factorials we just introduced, i.e., we just lack a factor of 2n choose n. So we can simplify the summation a little bit like so. The 2n choose n part does not involve I, so it is not summed over and put in front. And in the summation, one of the factors we call n choose I, the other n choose n minus I. Then the summation itself has a combinatorial meaning, choosing I objects from n, and then choose another n minus I objects from another set of n objects. So we are choosing a total of n objects out of a total of 2n objects. If we have a different value of I, that gives a different subset of ways to choose n objects out of 2n. So if we sum up all possible values of I, that should give us exactly 2n choose n, and we get the final expression for this return probability in 2D. In 3D, this is the 2nth step probability, but unlike last time where we have a simple closed form expression, there is no simple formula for this summation. Luckily, we only need to prove that the series converges to a finite number, so we can overestimate each term in a series, the idea being that if this larger series still converges to a finite number, then surely the smaller series has to converge. So how do we overestimate this thing then? The first step is similar to the previous 2D case. The denominator again has two sets of factorials, and so again, we want to have these two identical factors. But then again, these extra factors being left out would be grouped to form another 2n choose n. And so we obtain these different factors in a summation, like before. To overestimate this, we only overestimate one of the factors in the summation. More specifically, the overestimate is when I, j, and n minus I minus j are roughly n over 3. Of course, if n is not an integer, we can't do this, but we just want to make these three factorials as close as possible. But why is this an overestimate? If I, j, and n minus I minus j are not that equal, or more specifically, I is smaller than j by more than 1, then by making them more equal, i.e. making the smaller one bigger and the bigger one smaller, the value of this factorial thing would be multiplied by j over I plus 1, because I factorial and I plus 1 gives us y plus 1 factorial, and the j factorial in the denominator with j on top gives us j minus 1 factorial. So just by making these changes, the value changes by a factor of j over I plus 1. If I plus 1 is really smaller than j, then this factor will be larger than 1, and we can go bigger by this transformation. By repeatedly applying this equalization, we will eventually end up with the denominator being as equal as possible. This will be the largest possible value out of all expressions of this form. What we have shown, therefore, is that we can overestimate the summation by replacing the red box by equalizing the denominator, and the other terms are still intact. The final thing we need to manipulate is this summation. This again has some combinatorial interpretation. Remember that the number of return paths for a specific value of I and j is this 2n factorial divided by all these factorials. And similarly, if we only allow 3 directions totaling n steps, then the total number of paths given this specific set of values of I and j is the factorial thing that we are summing up. So if we were to sum up all these for all possible values of I and j, we would have gotten the total number of paths without any restrictions on number of steps for each direction, just that altogether there are n of them. In that case, the total number would be 3 to the n, where the n stands for having n total steps, and each step has 3 possible directions to be chosen from. So when we go back to our overestimate of the 2nth step return probability, we can replace the yellow box by 3 to the n. This 3 to the n can combine with a 1/6 to the 2n in front and give 1/12 to the n, which we like to separate into a quarter and a third, both to the n. For reasons that will be clear, we separate these two factors like so. Okay, so just to recap what we have so far, in 2D, we want to prove that the origin is recurrent, and we have deduced early on that means the sum of these 2nth step return probabilities diverges. All we have done is to compute these probabilities. Now in the case of 3D, we want to prove that the origin is transient, then that in turn means the series needs to converge. We have computed an overestimate and want to prove that the overestimated series also converges. But how do we know the series produced by these terms diverge or converge? Let's focus on a 2D case. This will be the final stretch. First off, we rewrite this as a square of something. This part comes from the power of 1/4, and the other part comes from the 2n choose n. Next, we expand the factorials in the numerator and the denominator. Notice that in the denominator we have 2n factors of 2, and there are also exactly 2n numbers in the rest of the denominator, so we can distribute those 2n factors of 2 into those 2n numbers. Then we can eliminate the even numbers from both sides, and we will get all odd numbers in the numerator, even numbers in the denominator. But we still have the square out there, and so we need to have 2 copies of each number. Because the first number is a 1, we can essentially slide the numerator by 1 place, and the value will still not change. Just to make our pattern continue, we multiply and divide by 2n plus 1. This first part might be familiar because it is the truncated Wallace product. Don't worry if you don't know anything about the Wallace product because we don't need to use that. Note that all of these pairs of fractions have this form, which amounts to 1 minus 1 over 4k squared. This is larger than 1 minus 1 over k squared because we have subtracted more from 1. Very similarly, we can express this in terms of a product of 2 fractions. So by replacing each pair of fractions by this form, we should get something smaller. The good thing about this is that these 2 fractions in the middle will cancel out, and so will all the other pairs, and we are only left with these 5 fractions in the end. We do a final underestimation with these fractions. First off, this n plus 1 over n is greater than 1, and 1 over 2n plus 1 is greater than, say, 1 over 3n. So finally, we have an underestimate of this 2nth step return probability to be 1 over 8n. That just means the series will have to be greater than the sum of 1 over 8n. This is just a constant times the harmonic series, so it diverges. And this larger return probability series will also have to diverge as a result. That is just a 2D case. We have manipulated this formula for the return probability to prove that the series diverges by comparing it to the harmonic series. This shows that the origin is recurrent. Now what about the 3D case? This part of the overestimate looks very familiar because it is a square root of the previous 2D case. In the previous 2D case, we obtained this truncated Wallace product. Previously we underestimated, this time we need to overestimate it. each pair of fractions gives a product less than 1, so we can overestimate each of them to be 1. And the final 1 over 2n plus 1 can be crudely overestimated to be 1 over n. So overall, in the 2D case, we could have also overestimated it to be 1 over n. So this square has an overestimate of 1 over n, which implies that 1/4 to the n times 2n choose n is smaller than 1 over square root of n. So in the overestimate we calculated for the 3D case, this part is smaller than 1 over square root of n. For the other part, we assume that n is a multiple of 3. Similar arguments if not. So if it is 1 more than a multiple of 3, then increase one of these to become k plus 1 factorial, and if it is 2 more than a multiple of 3, then make 2 of these k plus 1 factorial. But let's focus on the n equals 3k case. Similar to the previous computation, we again distribute those 3k factors of 3 into all of the factorials in the denominator, giving us all multiples of 3 in the denominator. And then we cancel out one copy of all multiples of 3 on both sides. You can then decompose this into a product of lots of fractions. And very similarly to what we have done before, slide the factors in the numerator by one place and use the same trick to multiply 3k plus 1 on both sides. And again, we note that each pair of fractions multiply to less than 1, and the final factor of 1 over 3k plus 1 is less than 1 over 3k. But n is 3k, so this is smaller than 1 over n. Together with the 1 over square root of n in front, this amounts to the overestimate 1 over n to the 3/2. Ultimately, we are looking for whether this series converges, and we have shown that the return probability series is less than this 1 over n to the 3/2 series. We know that the series converges, and because this is a smaller series, this has to converge as well. So we have finally proved that this series converges in the case of 3D. Now I did assume the knowledge that one of the series diverges and the other converges. We can use the same argument, given in what's called the Cauchy condensation test, and you can look for resources on it in the description. It's not actually difficult, just that to be honest, I did not plan on making a second channel video that long. Alright, see you next time.